Hello everybody. In this lecture we're going to be covering beam bending experiments or beam deflection, whatever you name it. I just made this 5-minute short video. That's the timeline for this experiment. It's straightforward and it's really quick experiment. So in this video we're gonna look at this beam bending equipment. This equipment is named Scott Beam Tester, and it uses aluminum beam specimen, and we are able to measure the deflection at 3 different locations. So the first location is 4 inches apart from the left end, and the second location that we're going to be measuring the deflection is 6 inches apart from the right end. Also, we're going to be taking the measurement from the midspan, which is in the middle of the beam. And the loading. Let's look at the loading scenario, how we're going to load this beam. We are using this hydraulic pump to load our beam. And as you pump this hydraulic pump, these two locations will be applying equal forces. Let's say if you load 300 pounds of load, 150 pounds will go to this end, the other 150 will go to this end. Also, we have a strain gauge monitoring system right here that is connected to the strain gauge located at the underneath at the bottom of the beam, and it's along the beam, and it will give us the deformation along the beam. So let's look at the sketch free body diagram that is on your handouts. You can find this handout on your Moodle. When you look at the schematic, you will see that the length of the beam 18 inches. So this beam spans 18 inches. Sorry. And the loading locations. We have 2 loading locations. Like I said, if you load them with 300 pounds, the P over 2 will go here, which is going to be 150. The other half is going to go to this location. And it is 7.5 inch from the left hand, first location of the loading, and the second location of the loading is 7.5 inches from the right hand. And you can see that this beam is symmetrical from the center line. This is the center line. And we'll be looking at the deflection at 6 inch right here, and 4 inch right here, and 9 inch in the middle. Also, we are given the cross-sectional dimensions, where we can calculate the cross-sectional area and the moment of inertia. Base of this beam is 0.5 inches, and the depth is 1.25 inches. And we will start applying 150 pound load, and we're going to go up 300 pounds, and then finally we will reach 450 pounds, and each increment we will be taking measurements at these 3 locations, and we will record this data right here in this table. I have already completed the experiments, and I have these measurements ready for you. Like I said before, that we are using Scott Beam Tester and strain indicator or strain monitoring system, as well as the ruler. I already measured that these dimensions are correct. Also, if you have already watched the videos on Moodle that was posted last week, there are 6 different videos, short videos from YouTube, very beneficial. It helps you to understand the theory behind it, and it simplifies the bending theory as well as the moment of inertia. Okay, so if you watched it already, you should know how to calculate the maximum bending stress using the equation right here, mc over I. That m stands for the moment, maximum moment along the beam, and c stands for the distance from neutral axis to the top fiber of the beam, 0.625 in this case, and the I is the moment of inertia. Also, we're going to be looking at the Young's modulus equation. We know that Young's modulus is the change in stress divided by change in strain. So in this case, during the experiment, since we are measuring the deflection, we will also calculate the deformation, which is the strain value, microstrain, during the experiment, and it will help us to calculate the Young's modulus at the end of the calculations. The bending stress is going to come from this equation. Once you calculate the maximum bending stress, you can input this value into the Young's modulus equation. And I have a sample calculation for one of these loading scenario where I calculate the deflection manually using conjugate beam method. That's a numerical technique. So I also want to simplify the theory and the logic behind this experiment. So let's see how I can simplify this beam bending theory. Okay. I also have a surprise for you guys. This is the simple design that I just put together before the lecture. This is a steel design structure, 3-story, and I want to show you guys why this beam deflection is important and what is the maximum limit, what is the maximum deflection that we can use when it comes to steel design or aluminum frame design, etc. Okay, let's get these notes. So why do we study the deflection of beams? Answer is super simple. Because we humans don't like bouncy structures. We don't want to drive across a bridge that flexes up and down as traffic rumbles across. Also, the paving surface of bridges, the brick faces of walls, and limestone facing of buildings will likely to crack and possibly deteriorate before the structural members fail in strength. Let's look at the steel angle spanning over the top of this garage door. So this garage door right here, there is a steel beam, steel girder crossing along the garage door, and it's holding up the brick layer on top of it. This design is most definitely deflection driven design. The steel angle could probably deflect 1 inch or maybe 2 inches. We know the fact that the steel is ductile and it can deform elastically and plastically before it fails structurally, However, the brick layer on top of it, it is not ductile. It is, in fact, is brittle. So if the beam deflects 1 inch or 2 inch, you will see the crack along the mortar joints and it will look terrible. I'm sure that you don't want to stay in this structure for a long time by knowing the fact that it will fail eventually. So another example, you can look at this rope bridge that the cat is passing across the bridge. In this case, this also shows the deflection is important when it comes to bridge. We humans, we can tolerate, or the animals, they can tolerate deflection or sagging of bridge, and we don't mind passing across the bridge, rope bridge, even if it's sag. But imagine that you are driving across the bridge with your truck or with your vehicle. It is not acceptable. It is unacceptable for vehicular traffic because it will vibrate and it will even deflect more because it is only working under tension. So as of now, we know that steel beams or steel girders, they can deflect 1 inch or 2 inch depending on the span length, but the brittle materials, on top of that brick or concrete or mortar joints, they cannot withstand deflection and they will crack. And in this design, I want to show you only this table. This is steel frame design preferences for AISC, American Institute of Steel, American Institute of Steel Construction. It is 360-10. They come out with these limits for dead loads, superimposed dead loads, for live loads, or total limit for all the loads. So when you look at the total limit, whatever is your length, span length of this beam, in this case, I think it's about 30 feet. So if it's 30 feet, your deflection should not be more than 30 feet times 12 inches. I need to convert it to inches. 360 inches is the total length of your beam, and divided by 360, which is the limit, L over 360. If you look at here, the deflection cannot be more than 1 inch. This is the design criteria. So if you're at the end of your design, once you design your structure, once you run the software and check for steel design, if your deflection is more than 1 inch, you will see that failure here. It's going to be in red, and it will tell you that you should increase the size of the beam or you should make some changes on your design. And your goal is to lower the deflection so that deflection can stand in the safe region. So from that design, we know the software can calculate the deflection in less than a few seconds and tell us if the design is working or not. But we have to know the theory behind it, and we should be able to derive the equations and calculate the deflection at any point along the beam manually. And this is the whole purpose of this experiment. But when you get a job in a consulting firm, you will learn how to use the software, and with the help of software, you're going to be able to check the deflections at hundreds of beams at the same time, and you will get your result. So we look at this equation at the beginning of the class, and I believe that you already mastered these equations from the videos that was posted on your Moodle. Okay, let's look at the conjugate beam method, which is a numerical technique to calculate the deflection. And let's see how we're going to calculate the deflection using the conjugate beam method. I'm sure you guys are already aware of conjugate beam method from Mechanics of Materials lecture, but if not, you can see the assumptions that we are using in conjugate beam method. So for conjugate beam method, the first assumption that we are making, that for a simple span, the conjugate beam is the same as the real beam. It's an imaginary beam, but we are assuming that it's a real beam. So the next step in our assumption, we need to load the conjugate beam with the M over EI diagram from the real beam and the real loading. So first, what we need to do, we need to draw the free body diagram of the beam that we are testing or we are designing, and then we should draw shear and moment diagram. Once you get your shear and moment diagram, you can use the moment diagram and you can load your conjugate beam with M over EI. So you don't know what E is right now because you don't know what the maximum stress is, but once you start solving the sample problem step by step, it will be way clear for you to understand what is M over EI or how it's working. And third assumption is the shear. Shears in the conjugate beam corresponds to rotations in the real beam. The fourth one, moments, which is the most important one. moments in the conjugate beam corresponds to deflection in the real beam. That's what exactly we want. So in order to calculate deflection, I have to solve for moment on the conjugate beam. So once I set up my conjugate beam, I should take a moment about a point. Let's say in this case we're gonna take moment about 4" and 6" and 9", and that moment is gonna tell us what the deflection is. The result is deflection. So if you look at this section over here, in the parentheses, we should compare these with deflection to those measured in the experiment, during the experiment. So this table is from the experiment. We have we measured the deflection at 3 locations and measured the strain along the axis, and we do it twice, and then we take the average. I also have the spreadsheet that is ready for you to use and check your results, and that spreadsheet includes the data points. You should also compute the percent error between the measured value, measured deflection, and the computed deflection. So if you look at all the way down at the handout, this is the sample calculation, but it's not quite clear to understand how the steps are, completed. But this is for 450-pound loading case. You can see that P over 2 is 225, and this beam is symmetric. You first draw the shear diagram, because you have 200. The shear diagram is positive at the beginning, because you have 225 pounds of load. Reaction force is going upwards, and you have your distance 7.5 inches, and then you have another 225 going down, which is, we assume that it's negative, and it's going to close the gap, and you have this rectangle here, and then right here in the middle there is no load application up until the second loading point, 225. So this is zero shear, and then that zero shear is 3 inches, by the way. Along the 3 inches length there is zero shear forces, and then you have another 225 going downward, that's negative, and you go 7.5 inches. Then you have other reaction forces going upward, which is positive, that's going to close the gap, and you have negative shear. So using this shear diagram, you can calculate the moment diagram. So a moment diagram is basically the area under the shear diagram. So once you do the calculations for the moment diagram, 7.5 times 225, you're going to get 1688 inch-pound moment, which is going to be the maximum moment that is required to calculate, is required in order to calculate the maximum bending stress. I mentioned that before, that moment here is the maximum bending moment. And over here you have your conjugate beam diagram that is loaded with M over EI, and M is going to come from this moment diagram, and E is unknown at this point, and we're going to calculate the E at the end. So in this diagram it is a little goofy, because usually the reaction forces we are assuming is going upwards because it's holding the beam, but in conjugate beam reaction forces are going downwards. So we have RC, reaction force 1 and reaction force 2, and knowing the fact that this beam is symmetrical, you can calculate the reaction forces easily from conjugate beam. It is 1/2 times 7.5 times 1688 inch-pound divided by EI. Like I said, we are keeping the E and I calculation till the end, and then once we solve everything, we're gonna plug in the modulus of elasticity as well as moment of inertia, and then we're gonna get our deflection. So 1/2 7.5 times 1688. How we get this number? Because if you look at here, there's a triangle right there, and in order to calculate the point load, or in order to calculate the or convert from distributed load to point load, we should calculate the area under the triangle. But that's not the only one. We have a small rectangle here, which is 1.5 inch times 1688, because maximum moment here is 1688. So your base is 1.5, your height is 1688. Same way for triangle, your base is 7.5, your height is 1688. You should divide it by 2. And knowing the fact that this is symmetric, RC is equal RC1 here. Let's say this is the reaction force 1, this is reaction force 2 for conjugate beam. They are equal due to the symmetry. This will give you, this calculation will give you the reaction force on the conjugate beam, which is 8860 inch cube pounds divided by EI. Now we're going to use this assumption that we made over here to calculate the deflection. So the assumption was the moment in the conjugate beam corresponds to deflection in the real beam. So if we calculate the moment right here at 9 inch, which is the center of the beam, midspan, and when we take the moment, the result from the moment is going to be equal to deflection at the 9 inch for real beam. So to do that, I should use the reaction force for conjugate beam 8860 right here, and then I should convert that distributed load to point load for this triangle, and then I should convert the distributed loads from conjugate beam in this rectangular section to point load, which is 2532, and then take the moment about the 9 inch. So assuming that the moment is positive, right here I have the calculation, moment is positive counterclockwise. If you take the moments and if you do the calculations, you should get the moment at 9 inch, and that will be the deflection at the real beam in the midspan. For delta 6, you should do the same thing. Just take a moment about the 6 inch, and again convert the distributed load to point loads, and take into account the RC conjugate beam reaction force, and calculate for the moment. Then that moment calculation, the result will be your deflection at 6 inch. So you can also scale values for delta 9. And if you look at the loading case for 300 pounds and 150 pounds. Okay, let's look at the clear solution. That was not super clear, but this is my solution. This is very clear. So in the sample calculation, in this case, the load scenario that I'm using is 300 pounds. So first, calculate the moment of inertia. You already know that moment of inertia for rectangular cross section is b h cubed over 12. B stands for the base, h stands for the height, and once you plug in the numbers, you should get 0.018 0.0814 inch to the fourth. Then you should calculate the stress, but in this case, actually there was a mistake on that first section, stress calculation. This paper was submitted by one of my students. I checked it out, but I didn't pay attention to stress calculation right here. This just don't take into account this calculation. This is not the way that you calculate beam stress. This is just for the stress when it comes to axial forces. This is not acceptable, so do not take into account this calculation. But other than that, everything is okay. I checked the numbers. So let's look at this. Let's look at the free body diagram. We already went over the free body diagram. We are trying to calculate the deflection at 3 locations: delta 6, delta 9, and delta 4. And 300 pound is the loading scenario in this case. So PO2 is going to be 150, and you're going to calculate, you're going to solve for the reaction forces, reaction 1 and reaction 2. Due to the symmetry, they are equal. So R1 plus R2 is 300 pounds, and we know that R1 and R2 is 150 at this point. So when you look at the shear diagram, the same way, you have R1 150 is going upwards, which is going to give you positive shear, and then 7.5 inches you go right, and the 150 pound of load is going downwards, so it's going to close that rectangle. Then you have 3 inches over here. There's no load applied at this point, so it gives you 0 shear. Then again, the 150 pound is going down, negative shear, and you have the reaction 2 that will close the gap, and it will bring the shear to 0. So we have to do the calculation for moment diagram here. In this case, we are looking at the moment at 6, because we need the moment at 6 inch. We need the moment at maximum moment by here, 7.5, or it's going to be the same even if you take a moment here at 9 inches, because there is no change on moment due to the shear force, 0 shear force in the middle. Also, since we are calculating for the deflection at 4, we should note the moment on the real beam, well, at 4 inches. That is 600 inch-pounds. You can see the calculation here: 150 pounds times 6 inches is 900 inch-pounds right here, and moments at 7.5 is 1125 inch-pounds, and moment at 4 inch from the right hand is 150 pounds times 4 inches. It gives you 600 inch-pounds. Then we have to construct our conjugate beam based on the moment diagram, and we're going to load this conjugate beam with M over EI. So M is here, maximum moment is 1125, and we should calculate the moment at 6. We already calculated, but we're going to use it on the conjugate beam calculations. So again, we have to calculate first what the reaction force is. We know that RC1 is equal to RC2. We can calculate the same way that we did before: 1/2 times base times the maximum moment, 1125 inch-pounds divided by EI. Then we have a small rectangle right here, 1.5 inch, with the base of 1.5 inch and the height of 1125. That gives you the reaction force on conjugate beam. Then we have to convert that distributed load to point load in order to solve for deflection at 6 inch. So the point load here is half the 6 times 1.5 times 900 inch-pounds. So the 900 inch-pound comes from the conjugate moment diagram right here. We know that moment at this point is 900, and which is the height of the triangle. So base times height divided by 2, 2700 inch square pound divided by EI. This is your point load. Then if you take a moment about 6 inch, it's going to give you your deflection. This is your calculation right here. So deflection at 6 inches equal to moment at 6 inch. So taking a moment about at 6 inch, assuming the counterclockwise is positive. So you have negative 2700 inch square pounds divided by EI comes from the point loads at 6 inches, and you multiply by 2 because this is the distance. So 2 inches come from the center of gravity of the triangle. So if you look at the center of gravity of the triangle, it is at a distance from the right end is b over 3. The base, whatever the base is, in our case, the base of this triangle is 6 inches. So 6 divided by 3, 2 inches, and the point load is acting this way, upward at this point. So 2 inches right here, and it's gonna be going clockwise. That's the reason it's negative, because we assume that counterclockwise is positive. Then we have the reaction force right here, 5906.25 e squared pound divided by EI, and we have to multiply it by 6 inches. In this case it's positive because RC1 is acting, the moment created by RC1 is acting towards counterclockwise. Once you solve it, once you solve for the moment, you will get deflection. But in this case, we plug in our moment of inertia, result from moment of inertia, as well as the result from Young's modulus. So how did we do the Young's modulus? So if you look at the equation right here, Young's modulus, you should use the maximum stress, and you should divide the maximum stress by the maximum strain. One second. Right. Okay, so this is the equation that we're looking at. Once you calculate the maximum bending moments, which was 1125 right here, you plug into the equation, and you already know the distance from the neutral axis to the top fiber or bottom fiber, C. It is 0.625. It is basically 1.25 divided by 2. And the moment of inertia we already calculated at the beginning. It was 0.0814 inch to the fourth, and that this number is coming from the experiment. We measured the strain during the experiment right here, and then we log it with the corresponding loading. So for 300 pounds loading scenario, the strain gauge measure the strain at 904 times 904.5 times 10 to the negative 6 inch. We are measuring actually micro strain. That's why we have to convert from micro strain to strain, and micro strain is let me see. Micro strain is 904.5, and to convert it to strain, you have to multiply by 10 to the negative 6. So once you calculate your modulus of elasticity, you can go to your last step, and you can plug it into your equation, and you can check. Sorry, I don't know why it's happening. Okay, and then you can check your moments. In other words, your deflection on the real beam. That's your moment on conjugate beam, and deflection on a real beam. And you can see that in our previous year, the experimental result from this deflection from experiment, was 0.041 inches, and the calculation result from calculation is 0.039. So you can calculate the percent difference, and the equation is 100 times absolute value 0.039, which is the result from the calculations, computed result, computed deflection, minus the experimental result, and then you're going to divide it by the computed result minus the experimental result. That's 5%. So that's all about it. You should do the same calculation for delta 4. Take a moment about 4 inch right here, and take a moment at the midspan. So if you take a moment right here, it will give you a deflection at 4 inch, and if you take a moment right here in the middle, it will give you a deflection at 9 inch. Okay, so this is the beam bending results from the experiment that I ran a couple of days ago. Like I said, we run the experiment twice. Though this is the result from trial 1, and this is the result from trial 2, and then I take the average, and this is the final average deflections corresponding to 150 pound loading scenario, and this is the micro strain right here. Let's zoom in more. So this is micro strain value 460 in the sample calculation. For 300 pounds, what they use was 904.5. One second. But yeah, 904.5. It's pretty accurate. So for 300 pound loading scenario, our strain value measured 904.5, and for 150 pound is measured 470.5, and you have to multiply by 10 to the negative 6 to calculate the strain. So in practice, the magnitude of measured strain is very small, so it's often expressed as microstrain, which is strain times 10 to the 6, etc., etc. This is the reason that we have to multiply by 10 to the 6. So once you do your calculation for 150 pounds, you should tabulate your result right here. You should calculate your modulus of elasticity, and you should calculate the deflection at these locations. So for your report, you should submit at least one sample calculation, and in this case, I want you to calculate the conjugate beam results, deflection at delta 9, delta 6, and delta 4 manually using the conjugate beam method. And you already seen the sample calculation, how to use the conjugate beam and how to. So you should be able to calculate the deflection at 3 locations using the conjugate beam method and the sample example that I walk you guys through. Once you finish your calculation, you can check your results using these equations. These equations are given to you to check your results. So if you don't submit your hand calculation, you're not going to receive credit for the sample calculation section, which is the 30% of your overall grade, which is the 30% of your overall grade on this report, because I want to see your work. This is simple and easy way to calculate deflection. And like I said before, this equation is derived by the conjugate beam method. So it uses conjugate beam method, but it's simplified version. If you pay attention to this equation, you can see that EI at the denominator and F times A, and F times A force multiplied by distance. A is the distance. That's the maximum moment. That's what we calculated. So it's M over EI is used here. So instead of going drawing shear and moment diagram and following the steps of conjugate beam, you can easily calculate your deflection, maximum deflection right here, 9 inch. Deflection at 9 inch using this equation. These are the equations to calculate the shear and maximum moment right here, FA. And if you're trying to calculate deflection between 0 and A, in this case our A is 7.5. Look at your first handout right here. 7.5 is the distance from the end of the beam to the point load. That's the A. So if you're trying to solve for the deflection at 4 inch or 6 inch, this is the equation that you should use. So once you complete the sample calculation and calculations for 150 pounds, you can use these equations to calculate the remaining ones, or you can scale up the values. So this is the table that I created. So if you change the loading to 150 pounds, and you have the force 75 pounds, and the length was 18 inch, and A was 7.5 inch, base is 0.5, height is 1.25, and this C is the distance from the neutral axis to the top fiber or bottom fiber. It is the half of half of the height, 6.625 inch. The maximum stress is calculated here. It is maximum moment multiplied by the C divided by the moment of inertia right here. Then you should enter your maximum strain corresponding to the load 150. That was 470. So if you enter 470 here, this is the strain. It's calculated right here. And the Young's modulus, it is a ratio of the stress and strain. That's calculated as well. And deflection at 9 inch is 0.023. Let's see, it is 0.023. It is actually 0.024, but in the first trial it was 0.023. So we are so close. And if you check the experimental value, 0.0245, and the exact value from is the computed value right here. You have 4% error. That's it. It is straightforward. So let's look at the guidelines. You have your guidelines. You should follow this guideline to develop your report. So you should follow, first thing first, you should follow the handout for the lab objective. The objective of this lab to measure the deflection at various locations and with various loading scenarios. For the theory, you can use the handout materials. Okay, so for the theory sections, you can use the handouts materials, identify all the terms in the equations. You can even use the previous videos that was updated on Moodle a week ago. And you can write in sentences as though you're explaining the theory to someone, right? So that I will have the impression that you understand the theory. Equipment is the same as the handouts, but added dial gauges and stationary micrometers. So I use micrometers to measure the deflection as well at the end of the experiment. Procedure described what we did. So if you want to see what we did, you can, I'm going to upload this video as well. You can look at the steps how I completed this experiment. I explained it at the beginning. It is straightforward. So in every load increment, I measure the deflection at delta 4, delta 6, and delta 9 manually, and I also get the measurement from strain gauge monitor to record the micro strain. For data and results section, remember that neatness is the part of exercise as well as the organization, etc. You should think as though you're explaining. You should think that as though you are a consultant and in a report. Example, you want a client to be impressed with your work and give you more work. Include the dimension of the bar, include the table of deflection data from the lab. You already have a bunch of the requirements over here prepared for you. You can use this template. Include the calculated maximum stress on the beam for 3 load values. Right here, maximum stress, and you can calculate it from here. But remember, you should calculate manually for 150 pounds. Section D, include the calculation of modulus of elasticity for each load value based upon strain data. You can calculate the modulus of elasticity based on each strain data right here. Then section E, include the predicted deflections based on the conjugate beam method. You can use the value for E, modulus of elasticity, that you get from 150, this one, yeah, 150 pounds load in your conjugate beam deflection calculations. So whatever is the E value you get from 150 pound loading scenario, you can use for the remaining ones. In your discussion below, tell me why you think I'm advising you to this. This is your job. Charts and tables, there are no charts and graphs. You should have only one table. Actually 2 tables. At the end, observed data and the calculated data. But you can include the observed data trial 1 and trial 2 as well. Sample calculation. This will be the most important section of the report. Calculate the moment of inertia for the bar. Show one calculation for beam stress and modulus of elasticity. Use the 150 pound data point. Calculate E based on strains for the other load points, but only show the results in your table. Show a conjugate beam calculation for 3 deflection points for the 150 pound load. So those 3 deflection points, delta 4, delta 9, and delta 6. The handout shows the calculation for 450 pound loads, and you can use this as a guide. And I also show you guys how to calculate the deflection using the 300 pounds load. However, I want to see the calculation for the 150 pound load. Include sketches of the free body diagram you use to compute your moment areas. For your information, you can skip the section E, 7-E. You have to recalculate E using your conjugate beam equations and the average observed deflection for each load case. That's not necessary. Again, your sample calculation should be handwritten. Please make them neat and readable so I can follow your analysis. Summarize your data and all calculation in a spreadsheet. The spreadsheet is already provided to you. Discussion and conclusion. Discuss the differences between the observed deflection data and the calculated deflection. Why will there be such variation in the values of E? With that being said, we can conclude this section. there is everything is covered right here. Perfect. So if you have any question, you can shoot me an email and we can set up a Zoom meeting, or we can have a phone call. I can answer your question on private Zoom meeting or on a phone call.